Good afternoon, everyone. 4 years ago, I was like some of you sitting on the other side of the screen, don't know anything about OpenFOAM. I was a totally pure beginner. But one day, my colleague Rui Song, the initiator of our OpenFOAM workshop, he showed me his simulation using OpenFOAM with hull waves acting on the ship. I found it's pretty cool because you can see the changes of forces from the generated animation more intuitively. And this brought my interest in OpenFOAM. And I thought maybe I could use OpenFOAM in my own project to generate a more practical path for the unmanned ship to follow. So I started to learn OpenFOAM from Rui Song. And the more I learned about OpenFOAM, the more advantage I found for its potential applications. 4 years ago, 3 years ago actually, in 2018, UCL announced a doctoral skills program. And Rui Song generated an idea and asked me to apply the program together. And thanks for the program for giving us opportunities to teach simulation skills to people who are also interested in using OpenFOAM and promoting cross-subject projects with inspired research ideas. And you can see from the topics here, there were not so many people joined in the first workshop, and we were only in a small teaching room. However, in 2019, our second OpenFOAM workshop generated more interest, and we moved to a bigger lecture theater, and our community became much more stronger. Last year was a difficult time to all of us, I think, and we have to stop the workshop because of the pandemic. So when I was invited to the third OpenFOAM workshop today, I was very excited and glad to join without hesitation. As the first session of our tutorial today, I would like to share the basic knowledge with you about how to use OpenFOAM and some points that need to be paid attention at the beginning of the study. I hope after this session, you will get familiar with OpenFOAM. Before we start to learn a software or an application, we need to understand 3 questions. What is it? Why should we use it? And how to use it? For OpenFOAM, it is a numerical software for solving and analyzing continuous mechanics problems. The most popular is to simulate fluid flows, and this can be any fluid, like liquid or gas. It can also simulate solid mechanisms and fluid structure interactions. Recently, more and more people prefer to use OpenFOAM for their simulation because it can be applied in different research areas, such as physics and chemistry. By using OpenFOAM, it can help us better understand a physical process by situational results. For example, in the application of naval architecture, we can simulate the influence of different water speeds to a ship structure. And similarly, we can simulate the deformation of building under strong winds or even when typhoon comes. So it can help the civil engineers to design stronger buildings. OpenFOAM can not only generate figures, but also videos from the simulation results to help us better present and explain our work. For example, like a simulation represented in a video will boost up our presentation in the conferences or meetings, and it will give the audience a deep impression from the psychology perspective. Comparing to traditional mathematical solutions and experimental methods, OpenFOAM is more advanced, cheap, and convenient. For example, in combustion experiment, the temperature is usually very high, and if we can use OpenFOAM to do the test, it will be much safer for us. This slide here shows comparisons between the OpenFOAM software and the commercial software. So firstly, as I mentioned before, OpenFOAM is open source, and all codes and example scripts are accessible. But in most commercial software, we can only use the graphical user interface to build the simulation model. And secondly, OpenFOAM can solve almost all CFD problems, while the commercial software usually is designed for a specialized area to solve a specific case. Thirdly, OpenFOAM is convenient to our users to develop our own submodels. This means that if there is a function that you need to use, is not exist in OpenFOAM library, you can modify the source code yourself and to add such a function. However, for commercial software, new functions are only available when a new software version is realized. The advantages of using commercial software are easy to learn and straightforward to use. Comparing to this point, OpenFOAM is a bit difficult to understand and easy to causing bugs. So we have to get some knowledge of fluid dynamics and the C++ language because the OpenFOAM is written in C++ language. So our conclusion is that OpenFOAM is better for research and commercial software is more suitable for industrial usage. My talk before is a brief introduction about the OpenFOAM software. And now let's see how OpenFOAM solves a practical problem. And usually OpenFOAM simulation includes 3 steps. The first 2 steps are space discretization and time discretization. Space discretization is to divide a domain of interest into a number of non-overlapping cells. This is known as mesh. While time discretization is to split a process into a number of time steps. Usually, when we start to learn a process, we discretize the domain by a number of cells and get the solution of each single cell. And all these solutions will compose into the solution of the whole space domain. For example, this black object here, we can see that it forms by a number of single cells. However, it's difficult to tell whether this object is a diamond shape or a round shape. If we increase the number of cells, we can see more clearly that it is a round shape rather than diamond shape. This means that higher number of cells can provide better resolution. Time step is simpler to understand. It's like making a film. For a film is performed by many frames, consists of many frames. For example, the second figure here shows the process of a Superman landing on land and standing up. By dividing the process into different time steps, we can see the change of his actions during the process. If the total number of a process you want to simulate is certain, for example, 10 seconds, please ignore my bad handwriting. And if we divide the entire time into 100 time steps, and this means that the program will solve the result every 0.1 second. And if we divide the entire procedure into 1,000 time steps, this means that the program will solve the simulation per 0.01 second. Please note that when we discretize the space and time of interest, there is a trade-off between the number of cells and number of interests and the computational time. This means that higher number of cells and time steps can give us more accurate results that close to the real situation. However, it will take more computational time to solve the problems. Once we define the size of the cell and time steps, the last step for the OpenFOAM to solve the problem is to use the governing equations. The selection of governing equation is related to the parameters that are of interest. For example, the Navier-Stokes equations here can solve the problem of pressure and viscosity. And if we want to simulate the combustion problem, we can use the energy-related equations. Since we have understood the process of OpenFOAM simulation, now let's get ready for looking at a simulation case. To save the time, I will assume that you should have installed the Ubuntu system and the OpenFOAM software. If you haven't installed yet, you could just look how I operate first and install the OpenFOAM software after the workshop. And you can follow our installation tutorial or use the YouTube channel by Yusuf. He has a video can show you how to install the OpenFOAM software step by step. Actually, OpenFOAM can be installed on different operating systems like Linux, Mac OS, and Windows. But Linux has the best compatibility and covers all the functions of OpenFOAM. Therefore, we recommend to install the Linux system, namely Ubuntu, to operate the OpenFOAM. Now I'm going to switch my screen to the Ubuntu system. After we install the OpenFOAM, the files will be stored in the home folder called OpenFOAM. And if we open the OpenFOAM folder, you can see that under the tutorial file, there are many ready-to-use examples stored under this file. And this is fantastic to get started and familiar with OpenFOAM. Because in your own simulation, you can always modify your own code based on these tutorials. And this is convenient for our beginners. So we don't need to reinvent the wheel, write the whole piece of code. And here's a notification for you. When you're modifying a tutorial, it's better to first copy the example code to our own directory, which was created when you install the OpenFOAM software. For me, it's stored under the name you created and in the wrong folder. Today, we are going to look at an incompressible fluid tutorial case to see how an OpenFOAM simulation looks like, and we can do the simulation together. So if we go back to OpenFOAM folder and open the tutorial file again, we can go to the incompressible file and use the IcoFoam solver here. Look at the cavity example. We can see that there's 3 files stored in the cavity file: 0, constant, and system. The 0 folder will set the boundary and the initial condition of each of the variables in question. For example, the pressure and the velocity. And in the constant folder, it will define the properties of the fluid, like the viscosity and density of the fluid. While the system folder will solve the case, including space discretization, time discretization, and the solver we used. As I said before, the first simulation step for the OpenFOAM to solve the problem is the space discretization. The generation of mesh is realized by a file called block meshdict, which is stored on the system folder. So if we open the file and double-click the block meshdict script, we can see the code as shown here. To generate a mesh, the first thing we need to do is to define the vertex of the mesh. We can see that in the vertex function, there are 8 vertices in total being defined, because in OpenFOAM, it uses 3D Cartesian coordinate system to represent the world. Therefore, each vertex has 3 values representing the x, y, and z coordinates respectively. Once all vertices are defined, they are numbered in order and will start with 0. All the 8 vertices can form a hexahedron, which is defined in the blocks function. And this is our computational domain, like this. In the next bracket, 2021 means the hexahedron will be discretized into 20 cells along the x direction, 20 cells along the y direction, and 1 cell in the z direction, respectively. And this tells us this is a 2-dimensional problem. We can only put 1 cell in the inactive directions. Therefore, the total domain will be divided into 20 times 20 times 1, which equals to 400 cells. And the simple grading brackets here means the size of the mesh we just defined are uniform on all XYZ directions. Changing the value here can gradually increase the size of the cells along the direction. For example, if we change it to 511, this means that the last cell, X19, is like 5 times larger than the first cell, X19, X0 along the X direction. Now in the boundary function, we can see that a face is defined by every 4 vertices. In this simulation, there are 1 moving wall, 3 fixed walls, and 2 front and back faces are defined. So there are 6 faces being defined in total, and these 6 faces form a cavity. After we define the simulation domain, we need to define a problem in a physical way to make the simulation practical. This is known as initial condition and boundary conditions. Initial condition is straightforward to understand. It defines the initial configuration of a simulation, namely when time equals to 0. While boundary condition defines how the simulation being pushed forward per time step. The initial condition and boundary conditions are defined in the script stored under the 0 folder. And I can show you in the Ubuntu system like this. So if we go back to the cavity folder and open the 0 file, we can see that there are 2 scripts with pressure and velocity. So let's take the velocity script as an example. Because we have defined 3 kinds of boundaries in the block meshdict file, moving wall, fixed wall, and front and back walls. So here we need to define the boundary conditions for each of the faces. In the code dimensions, here it defines the unit of the variables. So therefore, the unit of velocity is meter times signal of power minus 1, which means that the unit of velocity is meter per second. We can see from the code that the moving wall boundary always have a constant velocity of 1 meter per second along the x direction, but the fixed wall doesn't have a velocity. And the empty boundary condition is usually used on the inactive boundaries for the 2-dimensional problem, and which can be understood as no solution is required along the z directions. So until now, our simulation model has been set up and can be understood as the fluid is initialized as static with no velocity in the cavity. And then the upper wall will start moving towards the right-hand side with a velocity at 1 meter per second, while other walls will keep fixed. The upper moving wall will change the status of the fluid inside as the fluid has viscosity. So if we run the simulation, OpenFOAM will tell us what would happen in such cavity. Before we start simulation, the last step is to select a proper solver. Under the system control dict file, if we go back to the Ubuntu system, we can see a script called control dict. And if we open it, we can see the application of the solver and the start and end time being defined in this script. Usually the name of an OpenFOAM solver will be usually end with the word form with the uppercase F, and the prefixation depends on the solver type. So for example, the interFOAM is a solver to solve the fluids, to solve the two incompressible fluid simulations, and FSIFOAM is to solve fluid structure interaction problems. Because in our case, we focused on a single incompressible fluid problem. So here we choose the ICOFOAM as our solver. In the code, it defines the start time and the end time with 0.5 and 0 respectively. So therefore, the total runtime is equals to the end time minus the start time, which is 0.5 seconds. In the code, the size of the time step here shows is 0.005. And you may have a question, how can we choose a proper time step size? There's a rule marked in the red box. The Coulomb number C should be smaller or equal to 1 in order to achieve better accuracy and stability of the simulation. Therefore, we can get that the delta t, the time step size, should be smaller or equals to delta x divided by the velocity u. In our previous definition, the delta x should be the size of the mesh D divided by the size of the cells, the number of the cells. And in the previous script, the size of the mesh is defined as 0.1. And this can be found in the first line of the script. In block mesh dict. Here, you can see that the scale shows 0.1. This means that the size of the mesh is 0.1 meters along the x and yz directions. And because we have 20 cells along the x direction, therefore, our delta x equals to 0.1 meters divided by 20, which is 0.005 meters. This will give us the selection of the delta t. So the delta t should be smaller or equals to 0.005 divided by the velocity 1 meter per second, which is 0.005. So in the code, 0.005 should be fine if we choose this time step size. And if we have the because the total runtime is 0.5 seconds, therefore we use 0.5 divided by the time step size. We will get 100 time steps in total. So if we decide to save the results every 20 time steps, we will get 5 results after simulation is finished. Now it's time to run the simulation. We will need to run the simulation step by step from the terminal window. Therefore, if we go back to the Ubuntu system again, we can press the our key button, Ctrl-Alt and key. And this will open the terminal window. As I said before we run the simulation, we need to copy the original code into our own directory. So we copy the folder cavity into our own run folder. And once the copy and paste procedure are done, we can go back to the terminal window and go to the directory where we saved the file. So to do this, we need to type the command cd $ and f4 _9 run / cavity. And to see if the files have been copied successfully, we can use the command ls to check the list in that folder. And here we can see that there are 3 folders: 0, constant, and systems, which are all the files we need. This means that we can do the following procedures. And the next step is to build the mesh, and the command will be the block mesh. After the mesh is generated, you can see from the terminal window with the information of the mesh. And the next step is to launch the solver. Do you still remember the name of our solver, which is OpenFOAM? So we type in the terminal window command OpenFOAM. And once finished, you will have all the results at every 0.005 seconds. But from the terminal window, it's difficult to tell what the simulation results look like. Therefore, to view the mesh we generated and the simulation results, we can use a post-processing tool supplied with the OpenFOAM software called PyroFOAM. And to open the PyroFOAM, we can just type the command with the name PyroFOAM. Please remember that always the F is the uppercase. After press enter, now we will enter the PyroView window. Here in the pipeline browser, you can see that it opens the cavity.openFOAM, which is the module of our simulation case called cavity. And then we click apply button. And in the image window, you will see the domain of our cavity. To view the mesh, we can go down to the display panel and change the representation to surface with edges. And this will show the mesh we just created. In OpenFOAM, you can change the color of the representation. For example, if we want to change the color of the mesh, we can click the edit button and change the color to the one we prefer, for example, green color. And also we can change the lines of the mesh. And if we scroll down, we can change the edge styling. For example, maybe white. so you can save the image of the mesh we just created. And the next thing we want to look at is to view the results of the pressure. To do this, we can change in the property panel. If we go back and change the representation to surface and select from the .p from the coloring list, and this will show us the results of the pressure. And the pressure field solution has, as expected, with a region of low pressure at the top left of the cavity, and one of the highest pressure at the top right of the cavity, as shown here. And the dot pressure means that the pressure field is interpolated across the domain and gives us a continuous appearance. Instead, we can, if we change the icon to the cell ones, we can see that the coloring has been changed in the image results. A single value of pressure will be attributed to each cell, so that each cell will be denoted by a single color without grading. The color bar here can be changed as well. So if we drag and drop the color bar and make it in line with the image results, it will give us a nicer look. And if we go back to the coloring list, we can click the color bar item with small e. And in this window, you can change the text of the legend and also the font of the text and the color. So if we change the title to pressure to make it more obvious, change the color to black. And please remember to click apply before clicking OK. To better view the results, we can also change the background of the image by scrolling down to the property panel and change the color in the background list. Maybe select white. And usually when we write a journal paper or conference paper, the color more used in the journal paper is like blue-red rainbow color, while the default color in ParaView is the blue to white and red color. To change this, we can scroll up and click the button with little heart. Here you can change the color of the color scaling. And this will make the results look more formal. After we look at the results of the pressure, the next parameter we are interested in is the velocity. And the velocity is usually represented in vector because it has the direction and magnitude. So to view the velocity in vector field, we can apply two filters. The first filter is called cell center. And to apply the filter, we can go to the top toolbar to select filters and click search and type the cell center. Press enter. The filter cell center will make the velocity vector at the center of each cell. So to make it obvious, we need to click the apply button. And then we need to change the coloring to velocity. And like before, we need to change the color here. and the legend called velocity. Click apply. The second filter we need to apply is called glyph, namely the vector field. Before clicking apply, we need to do some settings. For example, in the active attributes, we need to change it to velocity and set the scaling factor to 0.05. This is the size of the vector, how it looks like. And if we change the color to blue and red rainbow, click apply. The vector field of the velocity will be shown like this. Let me make it in line with the image result. And from the image result, we can see that, as expected also, from the left to the right walls, the vector field indicates that the flow through walls changes like a inside like this. And if you want to save the results, we can go to the file tool to take the screenshot of our results. We give it a name. And if we go to the folder, we can see the results we just saved. And we can use the results, just directly copy it in our paper or slides. That's all my tutorial today, and thank you all for listening.